Welcome to Dataset Analytics. In Chapter 1, we understood the exact problem statement with respect to text classification, and in Chapter 2, we explored the entire emotions data, we visualized the data, and then we tokenized the entire data. In this chapter, that is in Chapter 3, we will be training a text classifier. So for this, we will be using transformers to train a text classification model. Now let's see what all approaches do we have to use transformers in order to train a text classification model. So there are two approaches. The first one is called as feature extraction approach or feature extraction technique. This technique uses hidden states as the features, and we have to just train a classifier on these features without modifying the entire pre-trained model. The second approach is called as fine-tuning transformers, wherein we have to fine-tune the entire transformer. In this technique, we train the whole model end to end, which also updates the parameters of the pre-trained model. Now let's see and implement each one of these in more depth. The first approach is called as transformers as feature extractor. Now it is very easy to use a transformer as a feature extractor. As seen in this figure, we use this last hidden state, or we use the output of this last hidden state as features for the classifier and freeze the entire model's body weights during training. With this method, we may quickly train a tiny or shallow model, which is a huge benefit. A neural classification layer or an approach like a random forest that doesn't actually rely on gradients could be used as a classification model. Now, since these hidden states only need to be pre-computed once, this approach is especially useful if you don't have huge GPUs available, or this approach entirely eliminates the use of GPUs. One thing we have to note here in this approach is the gradients are computed only in the green part. So in this part only, that is in green part, the gradients are computed and is called as the trainable portion. Now let's actually implement this approach 1 in Python. Initially we will implement the approach 1. That is using transformers as feature extractors. For that, we have to import something called as auto model class from the Hugging Face transformers. So let's import from transformers import auto model, and then we have to import the torch library. The transformer pre-trained model that we will be using in this tutorial is Distilbert base uncase. So let's define the model. Distilbert base uncased. Okay. Next, we have to check whether this system supports CPU or GPU. So here in this runtime, I have allocated it as GPU. So any GPU instance you can take. So device equals to torch dot device CUDA if torch dot CUDA a dot is available. Else, if the GPU is not available, then we have to simply take CPU. Okay. Now this PyTorch has been utilized to determine whether a GPU is present or not, and the PyTorch.nnModel.to method has been chained to the model loaded. Now this guarantees that if we have a GPU, then the model will consume GPU, else the model will be trained on CPU, but it will be much slower if we train the model on CPU. So let's load the model. Model equal to automodel dot from pre-trained Here we have to give model name and we have to put the device name. Let's run this block of code. So it's now downloading the model. The model size in hard disk is roughly 268 MB. Now let's extract the last hidden state. Extracting the last hidden state. Now tokenization, what we did in the last chapter was step 1, and this is the step 2 that we have to do. Now let's take an example before extracting the last hidden state of all the dataset. Let's take an example. So let's say text is equal to, this is an example. Text. Okay. Let's tokenize this. So inputs equal to tokenizer text and then return tensors equal to p2. Okay. Then inputs is equal to, we have to make the inputs or shift the inputs to the device that we are using. So if we are using GPU or CUDA, then the inputs will be directed to CUDA, else the inputs will be processed on CPU. So K V dot to device for K comma V in inputs dot items. Okay. Now we have to write with torch dot no underscore grad, no gradients, outputs equal to model double asterisk inputs. Now let's print, let it compute. Till then I'll tell you. Okay, so this is something error we have. Okay, so I think I have made one silly mistake here. Tensors. Okay, so till this part is executing, I'll tell you what this torch.nograd means. If we write here torch.nograd, it means that we have turned off gradients automatic calculation using the context manager torch.nograd. Now this is very helpful or useful for inference since it reduces the memory footprint of the computation. Now let's print the outputs. Okay, now this is the output. Now the output of the model may contain number of objects such as hidden states, losses, attention groups, and so on. Okay, but we can easily access the last hidden state. So in this output, which consists of n number of outputs like hidden state, losses, attention, etc., we only need last hidden state. Now this can be achieved using outputs dot last hidden state. Outputs. Okay, so this is the last hidden state. Now let's print the shape of this. So the shape of this is 1, 7, 768. Now let me tell you what this means. Now this hidden state has the following dimensions. So this is the batch size. This is number of tokens, that is 7 number of tokens, and this 768 is the hidden dimension. So I'll repeat it once again. This first 1 means batch size, 7 means number of tokens in the input, and 768 means hidden dimensionality. In other words, for each of the 7 input tokens, for each of the 7 input tokens, each token will be represented with 768 dimensional vector. Okay. Now it is a very common practice to use hidden state which is connected to CLS token, that is the start token, as the only input feature for classification task. Now this token may be extracted by simply indexing the outputs, and because it appears at the beginning of every sequence. So in order to access the CLS hidden state, we can simply use this one. So print outputs dot last hidden state of 0. This. So this is the last hidden state of the CLS token. Now this token will, this last hidden state of the CLS token will act as feature for classification task. Now let's print the size of this last hidden state, that is the CLS hidden state. Dot shape, and the shape is 768. So this last hidden state consists of only one word, that is CLS token, and the CLS token is represented with 768 dimensionality. Now let's compute the last hidden state of the CLS token for all the sentences in our dataset, that is for training, validation and testing. So let's define a function, extract last hidden state of CLS token, and this will be our input batch. It will take input batch. Okay, we will simply write inputs equal to k v dot toDevice, like we saw in this example token, for k comma v in input batch, or batch, we can simply write batch. Let's take input batch for more intuitive understanding. Dot items. Okay, if k in tokenizer dot model input names. Now let's extract the last hidden state. So with torch dot no grad So I have already told you why we are using torch.noGrad. We will extract the last hidden state, which equals to model. We will call model. Then we will provide inputs to the model, and we will extract last hidden state. Now we have got last hidden state for all the tokens, but we want last hidden state for only the CLS token. So hidden state for CLS token equals to last hidden state of 0, and then we will simply convert. So this last hidden state is currently in GPU, right? GPU device or CUDA device. We need to convert, or we need to bring back it to CPU, and then we have to convert into an NumPy array, because we will be requiring it more frequently while training, and we have to return here hidden state, which is this. Okay, now that we have defined a function which extracts the last hidden state of CLS token from this input batch, let's apply this functionality to entire dataset. But before that we need to do a minor thing. Our model expects the tensors as input, right? So the next thing to do is convert the input IDs and attention mask to the torch format. So emotions encoded dot set underscore format torch, and then columns equal to input IDs, comma, attention mask, comma, label. Okay. So now that we have done this one, let's extract the hidden state for entire dataset. So emotions with hidden states equals to emotions encoded dot map, as we will call this function this one, and then we will tell it to be to process it in batches. Let's run this. So now for the 16,000 training set, the extraction of last hidden state of CLS token is in progress. So after it process all the examples from training set, it will process all the examples from test set and also from validation set. Now this is the validation set, and finally the test set will be processed. Okay, now that we have extracted all the hidden states of CLS token from test set, validation set and train set, we have to create a feature matrix so that we can train our algorithms. Okay, so we need to create a feature matrix. For that we will require NumPy. We will use traditional machine learning terminologies like xtrain, xvalid, ytrain and yvalid. So here xtrain means features of the training set. So np.array, and we will use this emotions with hidden states variable of train of hidden state. Okay, so this hidden state is coming from this output, this hidden state, okay, which its function is returning. Similarly, we will do for xvalid, np.array, same thing we have to do. I'll just copy paste, and then instead of train we will simply write validation. Okay, now we have all the features for train and validation. Now we also should have the labels or target labels for this features. So ytrain equal to simple and this one np.array. I'll copy this, I'll paste this, but instead of hidden state we require label here, and we will simply do for, and we will similarly do for yvalid. Yvalid equal to np.array, and I'll copy this. Instead of validation, instead of here we will write train and here label. Okay, so for feature we have root here train and hidden state. For labels we have written here train and label. Similarly for validation set. Now we are almost ready with our data. Now we are 100% ready with our data. Now if we print the shape of this xtrain.shape, we can see here 16,000 and 768. Now this 16,000 represents the training number of sentences in the training dataset, and 768 means each sentence is represented with a dimensionality of 768 vector. And similarly you can get x valid and so on. Now let's print the shape of ytrain.shape. In ytrain we have got about 16,000 number of training examples, but here comma, there is an emptiness after comma. It is because there is only one label corresponding to each of the training sample. Now let's take a basic simple logistic regression to train our now let's train the model using simple logistic regression. So from sklearn dot linear model import logistic regression. Let's create an object. So let's say logistic regression equal to logistic regression. So this is the traditional machine learning algorithm which we are implementing here. So again we will use this particular object to fit the training data xtrain and ytrain, and again we will use this to evaluate. So score. So we will evaluate this on validation data x valid and y valid. Okay, let's run this block of code. Now if you are confused about what this particular object means, when to use fit, when to use score, you can go back to my previous videos, the another playlist which I'll link here, and you can go through it and understand what this exactly means. So here we have got a score of about 0.6075. Now let's plot confusion matrix. So let's plot confusion matrix. From sklearn dot matrix import confusion matrix display comma confusion matrix. Okay, so we will define a function here, plot confusion matrix, which will take y prediction as input. It will take y gold or y true, and the label names or the emotion names, you can say. Okay, so this confusion matrix equal to, we will utilize this confusion matrix, and then we will provide y pred, y and y true, and then in order to normalize the score, we can use normalize equal to true. Okay, then we will take another variable which is called display, and then we will use this confusion matrix display just to make it more aesthetically pleasing, and we will write here confusion matrix as CM and display labels equal to label names, and then we will plot this. So CMap equal to blues. Okay, and then we will assign a title, that is confusion matrix, and this is a normalized confusion matrix because here we have put here normalize equal to true, and then finally plt.show. Okay, now let's call this function and plot the confusion matrix. So before that we need the predicted values, right? So ypred equal to, we will call this object the trained logistic regression dot predict, and we want to predict on this x valid. Okay, we will get label names from the emotions dataset, which I have already told you in the chapter 1. Chapter 2, that is implementation. And then we will simply call this function plot confusion matrix. So ypreds, here y true means this one, y valid. Where it is y valid, this one, y valid. And then finally label names. Now let's see how our confusion matrix looks like. Some error we are getting. Ypreds. Oh, here ypred. Okay, ypred. Normalize must be one of two, predicted all none. Okay, let's see. So here normalize shouldn't be a boolean, it should be a string. And label names is not defined. Label okay, here it should be small. Okay, so this is the confusion matrix that we have got. Now one thing we can observe here is like anger and fear are the most, anger and fear, this one. So this is the true label and this is the predicted label. So here we can see that anger and fear are mostly confused with sadness. So because this value is bigger, so anger is mostly confused with sadness, as well as fear is mostly confused with sadness by this logistic regression. Similarly, we can see that this love and this surprise, so this love and surprise are most confused with joy. So love is confused with joy and this surprise is also mostly confused with joy. So that's it, guys. This is the first approach wherein we used transformer as feature vector to train normal traditional machine learning model. So this doesn't require any big machine or a GPU machine. Even on commodity systems or laptops, you can implement this kind of approach. So that's it for this third chapter. In the fourth chapter, we will entirely fine-tune the transformers. So till that, please like, share and subscribe to the channel. And like this video, comment on this video, give me a feedback so that I can improve in my next videos. Thank you.